the keyword group. If I want to do multicasting on LAN, then what I need to do is, first I need to make groups. Once I make groups, then I need to have a multicast multicast routing protocol to build that multicast tree. So I will not use the unicast routing protocol. That's what we are learning as part of planning of network architecture. We want to understand if we have to implement multicasting, so what are the ins and outs of that? That's what we are trying to understand. Okay, so I have groups. So whenever I will be needing to multicast group, this is my step one. If this is not there, no multicasting is there. So you have a protocol called IGMP, which we will look into, which is used to make groups. So first point which I need to do is to make groups. Once I have the groups, then I need to have a multicast routing protocol. So once I have a group, I need multicast routing protocol, and then I tell you what is the job of multicast routing protocol. The job of multicast routing protocol is this. So I draw you some parts of the multicast routing table. So I'm saying multicast routing table. So that would tell us what we expect from the multicast routing protocol. Let's say I will have source, group, incoming interface, and it's too small, so let me make it a little bigger, right? So I'm not able to write in this. So you have source, group, incoming interface, outgoing interfaces, and in a group, I may have a source, and they would be a group, and I may be not a source, but I will be a group. So I may have multicast, as I said, tree. So multicast trees could be of three types. One could be the source-based tree. So for example, source-based tree is that I have a source, and from this source, I'm having receiver 1, receiver 2, receiver 3. So these receivers always stay receivers, and this is always source. So source does not change, constant. Then when I'm making a table, I will put the IP address of that source. I will put the IP address of that source, and every member of the group will have the same IP multicast. That's how they become a group. That is how the class D is different from the other classes of IP address. So all these three will have same IP multicast address. And that address will come here. That address will be G. And the IP address of the source will be S. Right? So S will be an IP address, which is the IP address of source, whatever its TCP/IP configuration is having, and all the members in here, they would have the same IP address that would come from class D, would be starting from 224, whatever, right? So I will call this as source-based tree. As compared to that, I redraw the same tree. Now, these are 4 group members. Let's say node 1, node 2, node 3, node 4. So they run IGMP and they are a group. They run IGMP and they were also a group. Now, the difference between them is as they are on a Skype call. So any one could be there at a given point source, and all others would be recipients. So source is not a constant. Right? Source is not a constant. So then I would mention with star, I would say, you know what? Source does not matter because any one of them would be source. It doesn't matter. So group ID would say they all will carry same IP multicast address. So this is, I will call this tree source-based tree, and I will call this tree as group-based tree. And there is a second, there is also another type of tree that is called core-based tree. We'll talk about that later because I need to write more, so I have already a diagram. We will talk. And this is a variation of I would say it's a variation of not source-based, group-based tree. It's debatable. It's a variation of group-based tree or whatever. So we will talk about that. So main entries in your routing table would be either UART sources source-based or group-based. So the main distinction is when it's group-based, you would have a star. When it's source-based, you would have an IP address, normal unicast IP address. Then in order to make this routing table, the next thing we need to decide is the incoming interface. Incoming interface. So incoming interface is commonly in all the protocols is determined through what we call is reverse path forwarding. So you would see I am only writing interface, not interfaces, because your incoming interface will be always one. So how you would find out? You would find out through reverse path forwarding. So I give you an example how you do that. So let's say I am, this is a source. This source is having routers. And these are receivers. So reverse path forwarding says that if I'm a router, this router, let me use some colors. If this is a router, I have two options. I have a red option. I have a purple option. So I am going in the direction of, I want to go in the direction of source. So I would not take the purple path. So I will go, oh, this router can take me to source. And when I go to this router, I have only this. So this would take me source. So reverse path forwarding says, as first part, as part one, as part one, I want to go to source. So in order to go that, I have to make two things known to me. At every stage, I will choose reverse path interface and reverse path neighbor. Two things. So here I have two interfaces. I have an interface which is red and interface which is purple. I will choose one of them interfaces, and that would be my reverse path interface. And what will be the selection criteria for that? Which will take me to what is happening to my picture. So which will take me to the source. So I have two interfaces and I have two, let me color them as well. So I have this purple router and I have this red router, right? So now I have two interfaces to choose from, this router. So I will choose interface red. So my red interface would become my reverse path interface. And red router will become my reverse path forwarding neighbor. So I have to determine two things. So now let's say I'm here. So let's pick up some other color. I am this green router. So every router's job is to find out two things. So I have to find out an interface which would take me to source and a neighbor. So I have only one neighbor. So this interface will be my reverse path forwarding interface, and this neighbor, where this black one, this would be my reverse path forwarding neighbor. So whichever interface connects me to a device towards source, that would be my reverse path interface. And wherever it connect me would be my neighbor. If everybody does this, you can reach to the source. Now, if source has to send you something, source will send in the reverse direction of your exploration. Source will send transmission in the reverse direction of this exploration. For example, so now if source wants to send data, let's say to this, right? So what is my incoming interface? This is my incoming interface here, right? In here. So I have two interfaces. I have this red sort of and this purple. Whenever I receive data from source, always it will be received on this interface, which I'm making bigger with my pen, this interface. So I have three interfaces. I will always receive data from this interface. So what I would do, I'm a router, which will be part of a multicast. I will determine two things. I will determine my reverse path interface and reverse path neighbor. And once I have determined that, then I would know this. I would know which is my incoming interface. So if I name this interface, for example, I would say, let's say, this is I1, this is I2, this is I3. So these are the three, not the links, right? Links should not be, these are, right? So then I would say my incoming interface is I1. So here I would say my incoming interface is what? I1. So reverse path forwarding and IGMP for making the group and knowing the interface is common